All right, so let's start with section 1.1 in the textbook. So this is about propositional logic, and maybe a couple of words about this whole section is that it is going to be very sort of basic building blocks for logic and for doing rigorous math. So it's the kind of thing that we won't last very long talking about these things explicitly, but it will always be sort of implicitly very important in the arguments that we're making. And also, it will be a good sort of playground if you've never worked with any kind of proof stuff before. This should be like a nice basic place to start with how to reason rigorously. Is there a book to go along with the course? There is. Is this one, Discrete Mathematics and Its Applications by Kenneth Rosen. You can find the details of that on B courses. So let's start with some basic definitions. A proposition is basically our little unit of logic. So it's a declarative statement basically something that is either true or false. Please also let me know if you can ever not read my handwriting. That will be important for me to know. So for example, this is basic stuff, but 3 is greater than 2. This is a proposition, right? This is some fact that you can say is true or false. In fact, it is true. 3 is less than 2. This is another proposition. It is a statement that you can evaluate as true or false. And this one is false. It is sunny in Berkeley. This appears to be true right now. And just for our own, little help, some non-examples. So something like 3 plus 2, this is a mathematical expression, but it's not a statement that is either true or false. It's sort of just another number. So this is not a proposition. Or is it sunny in Berkeley? This is a question rather than a statement, so it is not an example. And as with many, many things in mathematics, we will denote these by letters often. We'll use letters as shorthand for propositions. And also, as with many things in mathematics, there are traditional letters to use for them, which are P and Q. And if you run out, maybe R and S, etc. So for example, if we say let P be the proposition that 3 is greater than 2, then P is true. So these are the basic building blocks of our logic, and we can combine them into more complicated propositions using logical operators. And we are going to run probably pretty quickly through a list of these. I don't want to spend too much time, but here are some important ones. And most of these mean basically what they mean in English, but I'll give a little bit more detail in a second about what they all mean. So here are some logical operators, which are things that you can use to combine propositions to make new propositions. So let's run down this list real fast. So not. This is what it sounds like, although I will say that it can, once you get into more complicated things, which we will do in the next couple of days, it can become quite tricky to figure out what the negation of something is. So let me say also this is also called negation and is sometimes denoted by this symbol. But in general, so the textbook uses these symbols and they're maybe good to be familiar with. So that's how you write not P. But I will generally prefer to use the English words because I think it's perfectly clear and fits better with our philosophy of making clear arguments. I think that symbols are useful in many situations, but this is not one of them where they really shine. So this is the only operator we're talking about that takes a single proposition. The rest of them, as you can maybe predict, will take two propositions, P and Q, P or Q, but not P only takes one. And we will write these things concisely in a truth table. So that is a thing that will look like this. So P is some proposition. It can either be true or false. And then not P is some other proposition. And the relationship between them is expressed in this table by writing that if P is true, then not P is false. And if P is false, then not P is true. So it just switches the truth value from true to false and false to true. Let's move on to and. So this is also called, whoopsies, also called conjunction and denoted by a wedge, which, again, I'm not going to use this very frequently, but you can remember it because it looks like an A for and. And this is what it sounds like as well. So let's just write down this truth table real fast. So now we have two propositions, P and Q, and they can take each true or false, but they can take a variety of different combinations. So there are now 4 possibilities for the combination of P and Q. And I will write them like this, and I'll always keep this same order: true, true, false, false, true, false, true, false. I encourage you to do the same just because it's convenient to have always be the same. Okay, and then P and Q. So P and Q is going to be true exactly when P and Q are both true, which is right here. Everything else, it is false. So for example, x greater than 2 and x greater than 3. This is true. So this is some proposition right here. Is true when both of these things are satisfied. That happens when x is greater than 3. All right, so here's an example where we need to do a little bit of departure from the regular language. So the normal English or gets basically broken down into two cases. The first one is called just or. If you want to be really precise, it is inclusive or, and denoted by an upside down wedge. And it's also called disjunction, but I will not be using those words, so let's not worry about it. And it means P or Q or both. This is the part that inclusive means. So just to write down this truth table real fast. I'm kind of flying through this, but I hope that I'm not going too fast. Can you read the last sentence again? That was a while ago. Feel free to repost that question, being more precise if you would like. Sorry, I missed it. I'm keeping the chat up so that you can drop questions in it, but as I guess is becoming clear, I might not see them immediately. It was then about building blocks and logical operators. I see. This one maybe. That was a mistake. Let's get rid of that. So what I was saying with that is that propositions are the building blocks of logic, essentially, and logical operators are the things that you can use to stick them together to create more complicated things. And also a question about, in England, the symbol for and is the symbol for a cross product. Do you know if they have a different symbol for and as a logical operator? I don't know. I'm not super familiar with this notation. As far as I know, this is the most common symbol for these things. But again, other people may use different notation, and my personal preference, which I encourage you to follow, is to use these ones, which are perfectly clear and unambiguous. Just write the word. So, P or Q. Let's fill this in again real fast. All the different possibilities. If you have a question, can you unmute and speak up? Yes? We'll see how that goes, but I think I want to try it out, so I encourage you to do that for now. For the conjunctive table, why is it false in the last one? Right here, I think you mean. And that is because P and Q does not mean that P and Q are the same. It means P and Q are both true. So in that case, they're not. So right, so let's fill in this truth table for or. So P or Q, so again, this is what it means. P or Q or both are true. Maybe I should write it like that. So where are the cases where P or Q or both are true? Well, here they're both true. Here P is true. Here Q is true. And this is the only time where they're not. So that is how that guy works. And closely related is the exclusive OR, which is written as XOR, sometimes pronounced like that. This is the exclusive OR. And I think the book denotes it by this product symbol. But again, I recommend using this term. And this is the same, except P or Q, not both, are true. So here's P, Q, and P XOR Q. So the only difference is that we're saying not both are true instead of allowing both. So here is a false, and then the rest of the times it's the same. So it's when exactly one of P and Q are true. So let's take a little break here and pick up again in a second.